So example 3 here, we've got a box cross-section that's subjected to a bending moment. The bending moment has components in the z-axis, parallel to the z-axis, and it has a component parallel to the y-axis as well too. So we'd call this biaxial bending, meaning that there are moments about the two orthogonal axes. And with that biaxial bending, this problem asks us for first, if the magnitude of this overall moment is 20 kip feet, what is the maximum stress on the cross-section? And alternatively, what is the maximum magnitude of the moment if the max possible stress or the max allowable stress is 12 ksi? So we'll go about that. First things first, we're going to want to write down our fundamental equation that's going to inform everything else that we do on the problem. So our fundamental equation here is that the normal stress due to a bending moment is equal to minus mz times y divided by iz plus my times z divided by iy. This will tell us the normal stress due to the bending moment at any location on the cross-section. There's one term that gives us the effects due to the z component of the moment, and there's another term that gives us the effects due to the y component of that moment. And the signs are very important. The negative in front of mz and the plus in front of my, that is simply an artifact of our right-handed coordinate system. And so as long as you have the coordinate system set up correctly, a right-handed coordinate system where x comes out at us, y is up, so positive z will be to the left. As long as you have that set up, and then you think of y and z as simply the coordinates of the points that you're interested in, then all of the signs will work out, where if you get a negative overall, that'll be compression. If you get a positive overall, that'll be a tensile stress. I'll also put up here, just because it will come in handy, that the moment of inertia is equal to the summation of I naught plus a times d squared. That's the definition for calculating the moment of inertia, whether it's about the z-axis or the y-axis. The moment of inertia is simply equal to the summation of all of the moments of inertia of a shape about its own centroidal axis plus the area of that shape times the distance between that shape's local centroid and the overall centroid squared. That's called the parallel axis term. We'll need that as well too. So with that in mind, let's just go ahead and do subpart A, where we're trying to calculate the maximum magnitude of the normal stress due to a given moment. So again, we have our fundamental equation up here. I need to know what mz is, y, iz, myz, and iy. So first things first, we can go in any order that we want, but I think it makes sense to try to calculate what is mz and what is my. And so we can see that based off the quadrant that our moment is shown in, we could break this down into a component parallel to the z-axis and a component parallel to the y. Now importantly, because m is shown in this quadrant, my z component will be negative. It's going in the negative z direction. This is positive z, this is negative z. Same thing with the my moment. For it to be the y component of this moment resultant, it's going to be pointed in the negative y direction. So we'll just make sure to keep those signs straight in our equations here. Other than that, it's simply some trigonometry. The horizontal component will be this hypotenuse m times cosine of 45. So mz equals negative m times cosine 45. Cosine 45 is just 0.707. And in our case, m is going to be equal to 240 kip inches. So I was given as 20 kip feet. I'm going to convert everything into inches and kips just to be in consistent units. And so I'll get mz is equal to negative 172.8 kip inches. Now for my, it's the same basic equation. We're doing sine of 45 instead of cosine, but as we all know, that is the exact same value. It just times m. M, as we know, is 240 kip inches. So it ends up being the exact same magnitude in the y, or negative z direction, and the negative y direction. Okay, so at this point we've got mz calculated, we've got my calculated, which is great. So then next step, again, any order will be fine. We're going to look, sorry, not part B quite yet. So here we calculated m. Now I'm going to calculate I. And so we need to calculate both the moment of inertia about the z-axis and the moment of inertia about the y-axis. Now, fortunately here, when we look at this cross-section, well, it depends on how you look at it. Some people might look at this and they might see 1, 2, 3, 4 different rectangles. The problem with that is that, say the bottom flange or the top flange, each of those have a centroid that's distant from the overall centroid of the cross-section, which is right here, which means that we'd have to deal with that AD squared term. Now I don't want to do that, so I'm going to think about it instead as a positive shape that's the extreme dimensions of this box. So I'm going to think of it as a box that is 10 inches wide and 16 inches tall, minus the effects of the void in between that's 8 inches wide and 14 inches tall. Now the reason that that's a benefit is because the centroid of each of these shapes, whether it's positive or negative, they line up. The centroid of the outer rectangle is in the middle. The centroid of the inner negative rectangle is also in the middle. And that means that we don't have any of the AD squared term to deal with. So with that in mind, the only thing that we need to do is keep track of how the moments of inertia about the y and the moments of inertia about the z-axis differ. Now, one other equation I could have put up here is that the moment of inertia of a rectangle about its own centroidal axis is equal to 1/12 base times height cubed. The base being parallel to our axis of interest, and the height being perpendicular to our axis of interest. Meaning, when my axis of interest is z, which is this horizontal axis right here, the base is going to be the 10 inches and the height is going to be the 14. So let's just write that out. It'll be the positive 1/12 times the b of 10 inches times an h of 16 inches, and that height's going to be cubed. Now minus 1/12 the base of the negative space, which is 8 inches, times the height of the negative space, which is 14 inches, that quantity cubed. And I'll write out the same formula for Iy. The difference being that now my axis of interest is y, it's in that direction, and so I'm going to make the base the 16 inches and the height the 10 inches. So the height now is 16 inches, the base is 10 inches cubed, and for the negative space, likewise, I'm interested in the y-axis, and so b is the distance parallel to that, which is the 14-inch vertical dimension, and the height is now the 8-inch horizontal dimension that will be cubed as well. Okay, so for IZ, I get 1,584 inches to the fourth. For IY, I get 736 inches to the fourth. And again, just to see if that is reasonable, looking at this cross section, all of the walls are the same thickness. They're all 1 inch thick, and this is taller than it is wide. So it makes sense that the moment of inertia about the z-axis that cares about that perpendicular distance from z will be greater than the moment of inertia about the y that cares about the perpendicular distance from the y, because that perpendicular distance from the z on average is larger than the perpendicular distance from y. So the moment of inertia about the z should be bigger than the moment of inertia about the y. So far so good. The result seems reasonable. Okay, so now we're at the point where we've got IZ, we've got IY, and now really all that I need to calculate are Y and Z. So Y and Z are simply the coordinates of the points that we're going to analyze to figure out what the stress is. And so we can pick any points that we want, but we could be a little bit strategic about it. I can already tell that the extreme locations, the corners, are most likely to have the extreme stresses. The further you get away from the neutral axis, the higher the stress magnitude is going to be. Now, just based off kind of experience, I know that the actual axis, the neutral axis for this moment resultant, as opposed to breaking them up, is going to be something maybe similar to the axis that the moment is acting in. It's going to be a little bit different, and that's fine. But roughly speaking, the neutral axis is going to be some sort of line that goes from the upper left down to the bottom right. Meaning, the points that are furthest away from that neutral axis, that combined neutral axis, will be point C and point A. And based off the right-hand rule, I can tell that if the moment is headed down this way, the right-hand rule is going to tell me that my fingers point into the screen at A, meaning it's going to have the highest compressive stress, and then my fingers are rolling away from point C, meaning that's going to have the largest tensile stress. So we could look at points B and D as well, but it's pretty clear that those aren't going to have the highest stress, because that's not the furthest away from what the actual neutral axis is going to be. Now, between point C and point A, there's not going to be any difference in magnitude of that normal stress, because this is a doubly symmetric shape. If we had a T-beam or something else like that, we might have to check both of these individually, but in this case, because it's doubly symmetric about the Z and the Y, the magnitude of the stress at C and the magnitude of the stress at A are going to be identical. One's just going to be negative, which would be at A, and one's going to have a positive stress, which is at C. So really, because this problem is asking us just for the absolute maximum value of the stress, either one is fine. So with that in mind, when we're calculating Y and Z, we can pick either the coordinates of A or the coordinates of C. It doesn't really matter. Okay, so let's just go ahead and pick point A. So Y of A is simply the vertical, the Y coordinate of point A. Now this is on the negative Y side, and it has a coordinate then of -8 inches. The Z coordinate of A is the horizontal coordinate of A. It's on the horizontal coordinate, yeah, point A. It's on the positive Z side, and it has a positive Z coordinate of 5 inches. So now I have everything that I need to plug it into this equation up here. And so the maximum magnitude of stress is going to occur at point A. And so I'll say sigma A equals negative mz. mz is negative 172.8 kip inches. And remember what I did here, there's a negative out here times mz, so I have a negative times mz, which is also a negative, so just keep in mind the signs are really important. My y coordinate is -8 inches. The moment of inertia is always a positive value. We calculated that earlier for iz. It's 1584 inches to the fourth, plus my plus my -172.8 kip inches times the z coordinate of a, which is +5 inches, divided by the moment of inertia about the y-axis, which is 736 inches to the fourth. And just look what we've got here. We've got a negative times a negative times a negative. This will be a negative value. We have a negative times a positive divided by a positive. This is going to be a negative value as well. And so when we calculate those, I don't have the terms individually added up, but I get negative 2.01 KSI. And that is going to be sigma A. And so more specifically, to respond to that question, the maximum magnitude then is just 2.01 KSI. So if we were being responsive to the question, it would just be, what is the magnitude? Magnitude always given in a positive value. But it happens either at A or at point C. Either one would have been fine to investigate what the maximum value is. So now we want to go through this problem kind of backwards and go for part B. So we first went through, we were given a magnitude of this resultant moment, and then we went through, we calculated our section properties, we calculated the extreme locations of the stresses, but we're given kind of the reverse here. We're asked to find what is the maximum moment if we know what the extreme fiber stress is going to be. So that means that we're going to erase a bit of what we've talked about here. And we're still going to use the same fundamental equation, but now we're going to look at part B. And we'll just erase some of this stuff and talk about what still we can keep. So part B, we're asked to find the maximum moment. And so our fundamental equation for calculating the moment about the z and the moment about the y still applies. The only difference is that now we don't know what the magnitude of the resultant moment is. So I'm just going to erase where we put in 240 kip inches before, and I'm going to leave it as minus m times cosine 45 and minus m times sine 45, meaning the moment now about the z-axis and the moment about the y-axis are simply going to be negative 0.707 times m, both of them, because it's cosine 45 and sine 45. So we don't know exactly what mz and my are in terms of like a discrete value, but we can represent it in terms of the proportion of m, the overall moment, that is in the z and the y direction. So at that point we do have mz as far as we can get it. We do have my as far as we can get it. And I would also point out that now we have sigma m, the largest normal stress that we can get is 12 KSI, and so I'm going to put that here as well too, 12 KSI. So I'll put kind of a squiggly for the moments because we've broken them down as much as we can. There's still some unknowns, but we've gotten them simplified as much as we can. Now, IZ and IY don't change based off the loading. That is a geometric property of the cross-section, and so that stays as it is. All right, so, and now for the extreme fiber locations for Y and Z, where the maximum stress is going to occur, again, same exact discussion that we had before. If the moment's acting here, then the extreme locations where the stress is going to be the maximum would be either point A or point C. We could use either one again. Again, all that we care about is the magnitude of the stress, and this is doubly symmetric, so the same magnitude of stress will occur at C and at A. And so it's totally fine to just keep on looking at point A. Point C would be fine as well. Maybe just for fun, we'll do point C. So the only difference is that we switch the signs on each of these. That's the only difference. Now we're going to get a positive stress, but even if we got a negative, all we cared about was the magnitude anyway. Okay, so we're going to use this equation again, but we're going to need to rearrange it a little bit once we've plugged in our values, because the maximum normal stress we know is 12 KSI, and that's equal to minus mz. mz is now variable. It's negative 0.707 times m times our y coordinate for point C, which is 8 inches, divided by the moment of inertia about the z, which is 1584 inches to the fourth, plus my, my being negative 0.707 times m times the z coordinate of point C, which is negative 5 inches, divided by the moment of inertia about the y-axis that we calculated earlier right here at 736 inches to the fourth. So what we have here is one unknown, m. And so I can factor that m out. I can then isolate it on one side of the equation by itself. So we can factor out the moment, the single unknown from this equation, and I will get 12 KSI equals m, the unknown, times the rest of the coefficients in this term. So 0.707 times 8 inches divided by 1584. So 0.707 times 8 inches divided by 1584 inches to the fourth, plus the rest of the coefficients in this term right here, which is 0.707 times 5 inches divided by 736 inches to the fourth. I just divide both sides by this term right here, and I get the moment equals 1433 kip inches. We could simplify it back down to kip feet if we wanted to. This is going to be approximately 120 kip feet, approximately. And that's going to be the maximum moment that can be withstood. Now, it's not surprising. Here, when we calculated the maximum normal stress due to a 20 kip foot moment, we got about 2 KSI. So some of you might have said, well, if we got 2 KSI for this, then in order to get 12 KSI, which is 6 times the stress, I would have just needed 6 times the moment, which is 120 kip feet, 6 times 20. So you could have gone about it that way, but because there is a linear relationship between moment and stress, you could have said, well, the relationship here would have to hold true for the relationship here. That would have been a fine way to go about it, but also going about it this way, if you hadn't done part A first, you would need to go through the equation just like before. So it's all about being comfortable working with an equation like this, whether you're going and calculating the stress, or if you're given the stress and you're trying to back calculate one of these other values, being comfortable with that's pretty important.